to this session on the stiffness method. We've now covered the full theory of the whole stiffness method. We've also finished coding. In this session, we will just look at the coding of another frame example, an indeterminate frame, which we will then validate using a structural computational tool. So join me and let's get into it. Before we begin, we'll recap the overall workflow for calculating reactions and internal forces using the stiffness method. We've already covered all the theory behind each of these steps in the previous lectures, including how to derive the stiffness matrices, how to assemble the global system, how to apply boundary conditions and compute reactions and internal forces. Those lectures also demonstrated how to carry out each part by hand, and they're all clearly titled according to the relevant topics. So you can revisit any of them if you want to revise the background or see some worked examples. This lecture, however, will focus purely on the coding implementation, taking the theoretical steps, translating them into a structured workflow. The process begins by dividing the structure into elements connected by nodes and calculating the local stiffness matrix for each element. We then assemble the global stiffness matrix and load vector, apply the boundary conditions, and solve for the unknown nodal displacements. From there, we can recover the support reactions and compute the internal forces for each element using the relationships we've already derived. Finally, we can check equilibrium to make sure that the structure is consistent, that the global and local forces balance. In summary, everything on this slide is a workflow summary of the method we've already developed theoretically. On this slide, we're outlining how we take the full workflow and follow it when coding the stiffness method for a frame. All of the steps come directly from the theory we developed in the earlier lectures, but the aim here is not to revisit the theory, but to show how we can implement it in a clean, readable coding script. You'll also notice a few small tweaks to the order of operations compared with how we originally developed the method step by step. When we were building the theory, inputs naturally appeared at the moment they were needed. In actual coding practice, however, that leads to inputs being scattered throughout the script. So in this final version, all of the input information is grouped right at the beginning. So things like the node coordinates, the connectivity, material and sectional properties, loading, etc. It makes it much easier to see where everything goes and adapt the code for other structures. And just to be clear, this reordering doesn't change the method at all. It's just cosmetic and just makes the script more user-friendly. The workflow then continues with computing element geometry, forming the local stiffness matrices, rotating each element into global coordinates, assembling the full global stiffness. We then define the global load vector, apply boundary conditions, and solve for the nodal displacements. And finally, we recover the support reactions, compute the internal element forces, and report the full set of results. This workflow is what we'll follow step by step in the coding example. And this is the full frame that we will be solving with our coding in this session. The geometry of the structure consists of two 5-meter bays with a story height of 3 meters. Each column is fixed at the base. All the members share the same cross-section, a 200 by 200 millimeter square section with a modulus of elasticity of 200 gigapascals. The frame, as you can see, is subjected to 3 different types of loading. A 5 kilonewton per meter horizontal UDL on the left-hand column, a 10 kilonewton per meter vertical UDL on the top beam, and a 15 kilonewton point load in the middle of the right-hand span. The key point about this frame is that it is statically indeterminate. Equilibrium alone is not enough to determine the internal forces. We need compatibility. In fact, this is a 6-fold indeterminate structure, meaning that there are 6 additional relationships required beyond simple equilibrium. It's exactly the type of problem where the stiffness method is most effective, because it naturally incorporates both equilibrium and compatibility through the displacement formulation. By implementing it in code, we can handle the degree of indeterminacy cleanly and effectively, without the algebra becoming overwhelming. We've already developed all the necessary theory in earlier lectures, deriving element stiffness matrices, transformation matrices, and the global assembly rules. So in this lecture, we can apply that full workflow to this realistic frame using coding. Before we start defining any structural data, the first step in our coding workflow is simply preparing the MATLAB file. This is mostly housekeeping, but it's an important habit to establish because it ensures that every run of the script starts from a clean, predictable state. So at this stage, we clear the workspace, close any open figures, and clear the command window. This prevents old variables or previous plots from interfering with a new analysis. We also add a header to the script to label the example and the units used, which is useful for when you build up a library of analysis files later on. Here we begin by entering the actual input data for the frame. The first part is the node coordinates. Each row lists a node number followed by its x and y coordinates in meters. This frame has 7 nodes in total, and you can see how each one corresponds to the diagram on the right. The coordinates fully define the geometry, the height of the stories, the beam spans, and the relative positions of all members. Below that, we define the element connectivity. Each row assigns an element number and specifies which two nodes that element connects. So for example, element 1 connects nodes 1 to 4, element 2 connects nodes 2 to 5, and so on. This tells the code exactly how the structure is assembled, which members are vertical, which are horizontal, and how the overall frame is linked together. Getting the connectivity right is absolutely crucial, because everything that follows, element lengths, angles, stiffness matrices, and eventually the internal forces, all depend on this information being correct. This slide essentially sets the foundation for the rest of the analysis. In this step, we assign the degrees of freedom to each node of the frame. For a 2D frame, each node has 3 degrees of freedom: the horizontal displacement u, the vertical displacement v, and the rotation theta. So we set num_dofs equals 3 to reflect that. Next, we count how many nodes and how many elements the structure has based on the input we just entered. The loop you see here automatically numbers the degrees of freedom for every node. Node 1 gets degrees of freedom 1, 2, 3, node 2 gets 4, 5, and 6, and this continues all the way up to node 7, which ends at degree of freedom 21. The table shown on this slide is exactly what the code produces. Each row corresponds to a node, and the 3 columns list its assigned degrees of freedom. On the right, you can see a visual representation of all of these degrees of freedom on the frame. Each orange diamond labels the rotational degrees of freedom, and the arrows indicate the horizontal and vertical degrees of freedom at each node. This helps us see how the mathematical structure of the stiffness method matches the physical behavior of the frame. The numbering of the system is really important because it tells the code where each element stiffness contribution belongs to inside the global stiffness matrix. It's really the link between the individual element behavior and the full structural system. In this part of the input, we define the material and section properties of the frame elements. These values feed directly into the stiffness matrices we derived in the theoretical lectures. Here we're using 200 gigapascals, which is typical for structural steel. We multiply that by 1 to the power of 9 to convert from gigapascals to pascals, because we decided to work in SI units. The line E equals E0 times 1's brackets 1 num_Ls simply assigns the same material property to every element. If you had different materials, you'd enter them individually instead. Next, we define the cross-sectional area A of each member. The frame has a 200 by 200 millimeters square section, so we convert that into square meters and again duplicate it for each element. We then define the second moment of area, or the moment of inertia, I, which is crucial for bending stiffness. For a 200 millimeter deep rectangular section, the expression is BH cubed divided by 12 gives the value shown. Again, this is converted to meters and assigned to every element. This slide highlights an important point. Although the geometry of the frame controls the shape of the displacement field, the material and the section properties control how stiff each element is. And that stiffness ultimately governs how the loads are shared between the members, something that equilibrium alone cannot tell us for an indeterminate structure. These inputs complete the basic physical description of the frame, and from here the code can begin computing element geometry and stiffness. Now we define the input loads acting on the frame. Just as with the material and geometric inputs, bringing all loads to one place at the beginning of the script makes the code easier to modify later. There are 2 types of loads in this example: nodal loads, forces or moments applied directly at a node. In this case, we have a single nodal force, 15 kilonewton downward force applied at node 6. Because the downward forces are negative in the global y direction, this appears as minus 15,000 newtons. The format here is node, force in x, force in y, moment. So we can also include horizontal forces or applied moments if we needed. And B, uniformly distributed loads or UDLs. These act along an element, not at a node. The code defines them in the element's local coordinate system, specifically as a load in the local y direction. A positive value means that the load acts in the local plus y direction, and a negative value means that it acts downwards relative to the local axis. So on element 1, we have a 5 kilonewton per meter downward load, and on element 4, we have a 10 kilonewton per meter downward load. These UDLs will be converted in the code to equivalent nodal forces using the formulas we derived earlier in the lectures. And the final piece of input data we need before moving on to calculations is boundary conditions. These tell the code which degrees of freedom are restrained, or in other words, which degrees of freedom must remain zero because of the supports. In this frame, all three supports are fixed at the base. And this means for each of the support nodes 1, 2, and 3, all 3 degrees of freedom are restrained. The horizontal, u, the vertical, v, and the rotation, theta. To implement this in code, we list the degree of freedom numbers that correspond to those restraints. Because we previously created the matrix n, which maps each node to its 3 degrees of freedom, we can simply reference them like this. n11, n12, and n13 restrain all degrees of freedom at node 1, n21, 22, and 23 restrain node 2, and n31, 32, and 33 restrain node 3. The diagram at the bottom of this slide highlights the supports with a familiar fixed base symbol and shows clearly which nodes are restrained. Getting the boundary conditions right is absolutely essential. Even a single misplaced degree of freedom can lead to incorrect displacements, reactions, or internal forces. So with the boundary conditions defined, we now have all the input information needed for the full stiffness analysis. Now that all the input data has been defined, the first computational step is to determine the geometry of each element. This includes the length and the direction cosines cos theta and sine theta, which tell us how the local element axes relate to the global coordinate system. We begin by creating arrays to store the length, cosine, sine, and angle for each element. We then loop through each element using the connectivity information defined earlier. Inside the loop, we extract the coordinates of the element's start and end nodes, and from these we can compute the horizontal and vertical projections dx and dy. The element length comes directly from Pythagoras. Next, we can calculate the direction cosines, so cos theta is dx over L, and sine theta is dy over L. These direction cosines are crucial because they are what allow us to transform the element stiffness matrix from local coordinates, where the formulas are simple, to global coordinates, which is how the structure is assembled. We also store the angle in radians using a tan 2 dy dx. This angle is useful for reporting or checking results, but we only convert it to degrees later if we want to display it. This entire step is automatic once the nodes and element connectivity are defined. The code effectively reconstructs the geometry of the structure, ensuring that even if we change the layout or add more elements, the stiffness computation remains correct. In step 4, we compute the local stiffness matrix for each element. This is the 6 by 6 matrix that captures both axial and bending behavior in local coordinates, exactly as we derived in the early theory sessions. The formula used here is a standard stiffness matrix for a 2D frame element with 3 degrees of freedom at each end, u, v, and theta. It includes the axial stiffness terms, EA over L, and the bending stiffness terms, which have EI over L cubed, EI over L squared, and EI over L. Inside the loop, we retrieve the length, area, and second moment of area for each element, and then use them to compute the matrix entries. The matrix is arranged so that the first 3 degrees of freedom correspond to the start node and the next 3 correspond to the end node. On the diagram below, that's degrees of freedom 1 to 3 on the left node and degrees of freedom 4 to 6 on the right node of a typical element. You can recognize the structure immediately. The diagonal terms contain the element's primary stiffness contributions, and the off-turn diagonal terms provide the coupling between translations and rotations. The signs ensure internal equilibrium and compatibility are maintained. This matrix represents the local behavior of the element, that is, how the member resists forces along its own axis. Now that we have the local stiffness matrix for each element, the next step in 5 is to rotate it into the global coordinate system. This is essential because every element is defined in its own local axes along the member, but the structure as a whole is assembled in the global xy coordinates. To do this, we use the transformation matrix T, which is built from the direction cosines we calculated earlier. For each element, the code constructs the 6 by 6 transformation matrix, which maps the local element degrees of freedom to global degrees of freedom. Once the matrix T is formed, the global stiffness matrix for the element is computed using the familiar relationship global K equals T transpose times the local K times T. This rotates the entire behavior of the element, axial stiffness, shear, and bending, and all the coupling terms into the global coordinate frame. The diagram on the right illustrates exactly what's happening. The element is oriented at an angle theta, and the transformation uses the cos theta and sine theta to express its stiffness along the global axes. This step is crucial because it allows elements of any orientation, vertical, horizontal, or inclined, to be combined consistently in the global structural system. With all the element stiffness matrices now expressed in global coordinates, we can assemble them into the global stiffness matrix for the entire structure. This brings together the behavior of every element and enforces compatibility between them. First, we need to compute the total number of degrees of freedom, which is simply the number of nodes multiplied by 3 degrees of freedom per node. Using this, we first initialize the global matrix K as a square matrix of the appropriate size. We then loop through each element. For every element, we extract the degrees of freedom associated with its 2 endnodes. These are listed in the matrix N that we created during the numbering stage. So the vector EDOFs contains the 6 global degrees of freedom affected by that element, the UV theta for one node and the UV theta for the second node. These degrees of freedom tell us exactly where the element stiffness matrix should be added in the global matrix. The line K EDOFs, EDOFs equals K EDOFs, EDOFs plus KLM places the element's global stiffness matrix into the correct location of the overall system, adding its contribution to any stiffness already present from adjacent elements. This naturally enforces the compatibility, so the shared nodes to form consistently, and the equilibrium, so internal forces in each element balance at shared degrees of freedom. The beauty of the stiffness method is that the assembly process handles all of this automatically. And once the global stiffness matrix is built, the entire structure is represented by a single unified system of equations. From here, we're ready to apply loads and boundary conditions and solve for the nodal displacements. In step 7, we assemble the global load vector F, which contains all the external forces and moments applied to the structure. We start by creating a zero vector with one entry for every degree of freedom. This ensures that the system begins with no loads, and we then add the applied forces one by one. The code first checks whether the variable nodal loads and UDL loads exist. These are what we put in the input. This is simply a safeguard. It prevents errors if the script is used for a structure with no applied loads, or no nodal forces or no UDLs, for example. In this example, we have nodal forces and UDLs, so the list isn't empty. We then loop through the nodal loads. Each entry specifies the node number, the horizontal, Fx, the vertical force, Fy, and any applied moment, Mz. Using the degree of freedom numbering stored in the matrix N, the code places each contribution to the correct entry of the global load vector. Here, the only nodal load is the 15 kilonewton downward force at node 6, so this appears in the global degree of freedom associated with the vertical displacement of node 6. At this point, the global load vector contains only nodal forces. In this part of the load assembly, we convert the uniformly distributed loads acting on elements to their equivalent nodal forces. Unlike nodal loads, UDLs act along the length of an element, so they can't be inserted directly into the global load vector. Instead, we compute their fixed end forces, rotate them into global coordinates, and then add them to the corresponding global degrees of freedom. The code begins by creating a container, FE loc all, to store the local fixed end forces for each element. Even though some elements may have no UDLs, this structure ensures consistency and makes later calculations cleaner. We then loop through the entries in UDL loads. Each row gives the element number and the load intensity acting in the local y direction. A downward load therefore appears negative. Once we know the element length, we can compute the standard fixed end force vector for prismatic beam under uniformly distributed load. This gives 6 local forces: shear forces, bending moments, and their equal and opposite reactions along the element. These local fixed end forces are added to FE log all for that element, which becomes especially useful if multiple distributed loads act on the same member. Next, we need to rotate these forces into the global coordinate system using the same transformation matrix T we used earlier for the stiffness rotation. This ensures the equivalent nodal forces align correctly with the global degrees of freedom. And finally, we insert the rotated forces into the global load vector at the appropriate degrees of freedom. This step completes the global loading for the structure, combining both nodal and all UDL contributions. On the right-hand side, the diagram shows exactly where the UDLs act, and the table shows the final assembled global load vector with all nodal and equivalent loads included. At this point, we now have the entire external loading correctly expressed in global form, ready for applying boundary conditions and solving the stiffness equation. At this stage, we've assembled everything we need: the global stiffness matrix K, the global load vector F, and the list of restrained degrees of freedom from the boundary condition input. Our goal now is to find the nodal displacements, which is the heart of the stiffness method. We begin by identifying which degrees of freedom are free and which are fixed. The setDiff command gives us the list of all degrees of freedom that are not restrained by supports. Those degrees of freedom are the unknowns of the problem, and using those we can extract the reduced stiffness matrix KFF and the matching reduced load vector FF. These correspond exactly to the equilibrium equation KFF times DF equals FF. We can then solve this system using the backslash operator, which efficiently handles matrix inversion and numerical stability. The result, DF, contains all the freed nodal displacements, both translations and rotations expressed in global coordinates. We then reconstruct the full displacement vector D. All the restrained degrees of freedom are set to 0 automatically because fixed supports cannot move or rotate. We then populate the free degrees of freedom with the values we just solved. On the right, you can see the final displacement vector printed in full. Each entry corresponds to a specific degree of freedom, and together they describe the complete deformation shape of the frame. Even small numbers can be meaningful because they encode how the indeterminate frame redistributes load and responds to stiffness differences. Once we have this displacement vector, everything else follows directly. Support reactions, internal member forces, bending moments, and shear forces. And this completes the solution to the global equilibrium problem. With the full displacement vector now known, we can move on to step 9, computing the support reactions. These are the forces required at the restrained degrees of freedom to enforce the boundary conditions. Essentially, the forces the supports must provide to keep those degrees of freedom fixed at 0. The calculation is straightforward and comes directly from global equilibrium. R equals Kd minus F. This gives the reaction force every degree of freedom in the structure. From this full reaction vector, we can then extract only the entries corresponding to restrained degrees of freedom because the reactions only occur at the fixed supports. These are the values shown in the table on the right of the slide. The diagram underneath the code highlights where those reactions occur: node 1, node 2, and node 3, the three fixed supports. You'll notice that some reaction values are positive and some are negative. This is purely a matter of sign convention based on the global coordinate directions. A negative reaction simply means the support is providing a force opposite to the positive global axis, which is completely normal and expected. These reactions are an essential part of checking the correctness of the analysis. When summed, they should balance the applied loads, confirming global equilibrium. And now that we have displacements and reactions, the final step is to compute the internal forces within each element. Step 10 computes the axial forces, shear forces, and bending moments that develop within the members as the structure deforms. Exactly what we need for structural design. We begin by preparing a container to store the local internal forces for each element. These forces will be expressed in the element's local coordinate system, which is the natural frame for interpreting axial shear and bending behavior. For each element, we do the following. Extract the element degree of freedom. So we pull out the 6 global degrees of freedom associated with the element start and end nodes, using the degree of freedom numbering matrix N. Extract the element nodal displacements. So using the displacement vector D, we assemble the element's displacement vector dE. We then use the transformation matrix T to rotate the global displacement vector into the local system, producing UL. We then retrieve the fixed end forces from any UDLs. These are the forces that would exist even if the element in displacements was 0, the standard fixed end forces we computed earlier for the distributed loads. And then we can compute the internal forces. The internal force vector is given by F local equals the local K times UL minus F0. The first term gives the elastic response of the element due to deformation, and the second term removes the fixed end forces so that the final result reflects the actual equilibrium forces within the member. The resulting 6x1 vector contains axial force and shear force at end 1, bending moment at end 1, and then axial force and shear force at end 2 and bending moment at end 2. These forces form the basis for plotting shear force diagrams, bending moment diagrams. With all element forces computed, we can now assemble the results and present them clearly. And the final step of the coding workflow is reporting the results. And this is where everything we've computed, geometry, loads, displacements, reactions, and internal forces are printed in a clear, readable format. Here the reporting does several things. Displays the global stiffness matrix, mostly for verification. We print basic element information. For example, in this case, we've printed out lengths and angles. This is to help confirm that the geometry was interpreted correctly from the input. We display the global load vector, which includes both nodal and UDL equivalent nodal forces. Seeing it printed out can make it easier to confirm that the loads were applied in the right direction and the right degrees of freedom. We then print the nodal displacement vector. This is a key output for the stiffness method. We show the support reactions. In this case, only the reactions at the restrained degrees of freedom are printed, and these should balance the applied loads, giving an immediate equilibrium check. And finally, we print the internal element forces. For each element, the code prints a full 6-component force vector in local coordinates. So, as we mentioned before, axial shear and moment at end 1, and axial shear and moment at N2. This is the information needed to construct axial, shear force, and bending moment diagrams. This slide shows two of the key outputs from the analysis: the global load vector F and the final nodal displacement vector D. On the left is the fully assembled global load vector, which contains all applied nodal loads and all equivalent nodal forces generated from the UDLs. On the right is the resulting nodal displacement vector, which is the solution to the reduced stiffness equation. Again, each entry corresponds to 1 degree of freedom. These displacements are the driving input for calculating internal forces in the next step of the analysis. Together, these two vectors form the backbone of the stiffness method output, one describing the external actions and the other describing the structural response. On this slide, we visualize the support reactions calculated from the stiffness analysis. The numerical values are shown in the red box on the left, and each corresponds to a restrained degree of freedom at nodes 1, 2, and 3. An important detail here is that the signs follow the global sign convention. So, for example, a negative horizontal force means that it's not in the positive x direction, but in the negative x direction, according to what we consider to be the global sign convention. On this diagram, we've drawn all the arrows in the correct physical direction. And that means that if we had a negative value, we just swapped the direction of the arrow, so it reflects the true direction of the reaction force or moment. This ensures that the diagram accurately represents the real behavior of the frame. And together we can see that these reactions satisfy global equilibrium. On this very cluttered slide, we are looking at the internal forces in every element of the frame. These are expressed in the local coordinates using the same sign convention we defined earlier in the course, which is at the top right of the slide. So, as I said, all forces and moments shown on the diagrams have been drawn in their correct physical directions. So that means that whenever a computation produced a negative value, the arrow has been flipped to match the true internal action of the member. Positive values will appear with the arrows matching the defined sign convention. The diagram makes the pattern of behavior much easier to interpret rather than looking just at the numbers. In the next couple of slides, we'll look separately at the forces that make up the axial forces, shear forces, and at the moments. So here we're just taking the forces which contribute to the axial behavior of the structure. We're comparing it with results generated using FTool, which is a well-established free structural analysis program, which you can see on the bottom right. To make the interpretation intuitive, all arrows in the diagram, as before, are shown in their true physical direction. Compression is drawn pushing the element and tension is drawn pulling away from it, so any negative value from the calculations already has its direction flipped accordingly. What we see is completely consistent with the applied loading. The left column carries significant compression due to both vertical UDL and the lateral load. The central column carries the highest axial force as it supports the majority of the roof UDL, and the right column carries a smaller vertical reaction and therefore smaller compressive force. Across the top beams, we can see axial forces induced by the distributed loads introducing horizontal thrust. And we also have the same axial forces plotted using FTool. You can see that the magnitudes match, the signs match, and the overall distribution along the structure is identical. This agreement confirms that our implementation of the stiffness method is producing correct axial force results. Checking results against an independent tool is an important validation step. It reinforces that our sign convention has been applied correctly, our transformation and assembly procedures are accurate, and the axial components of the internal force vector have been extracted correctly from the local coordinate system. Altogether, this gives us confidence not only in the code itself, but also in our understanding of how axial forces develop in indeterminate frames. In the same manner, we can look at the shear forces produced from our stiffness method code and compare them with the benchmark values from FTool. As with the axial results, all shear arrows here represent the true physical direction of the shear force in each element. Any negative values from our code have had the direction flipped accordingly. And this means the diagram reflects the actual internal actions within the structure, not just the sign of the computed numbers. When we look at the pattern of the shear forces, everything agrees with the applied loading. Below we have the shear diagram produced by FTool, and we can see that the comparison works. The magnitudes match and the sign matches. This confirms that the shear forces have been computed correctly, and that our sign convention and transformations were applied properly, and that the fixed end contributions from the distributed loads were included in the right way. It also reinforces that the code is capturing shear behavior of the indeterminate frame as expected. However, we must note that in the stiffness method, we only get values at the ends of the nodes, so we do not see, without drawing the diagrams, what happens in the middle of an element. And finally, we can look at the bending moment results. As before, every moment arrow shown here reflects the true physical sense of bending in each element. Any negative moment values from the calculations have had their direction flipped in the diagram to show the real bending action on the member. When we examine the pattern of bending moments, everything is consistent with the loading and support conditions. Below we have the bending moment diagram produced by F-Tool, and the match works as well. This agreement confirms that the rotational degrees of freedom, the element stiffness matrices, and the transformation into local coordinates have been implemented correctly. It also shows that the fixed end moment contributions from the UDLs have been fully accounted for. Again, we must note here that the moments given in the stiffness method are just at the nodes, so just at the ends of the elements. We don't know where the maximum moment, for example, in element 4 along the UDL is. We would have to consider that in a different method. But overall, this comparison gives us strong confidence in the correctness of the internal moment calculations, and more broadly, in the reliability of the stiffness method code for analysing indeterminate frames. And that concludes the stiffness method for frames. We've been through it all: the theory, the code implementation, and now another example. I hope you've enjoyed it, so go practice some more. And even if you didn't, it's worth maybe putting in your own example to see how this works and how it all ties together. Thanks for joining me.